Let's look at the effect of end conditions and column buckling in today's lecture. In our previous lecture, we derived the value of the critical buckling load PCR and the critical buckling stress sigma CR for an ideal column with pin-jointed ends at both ends. That was the very basic end conditions for a given column, and in actual, the end conditions may differ very much in contrast to what we assumed in our previous lecture. And one example of such actual end condition is shown in figure A here, in which the column that we have here, at its top end, it is framed into a beam section, and that beam section is being acted upon by some magnitude of uniformly distributed load, whereas at the bottom section, our column is being held firmly on a large substructure, and this substructure may be any RCC pedestal or RCC column, and the column is being bolted to this large substructure here. So these end conditions that we have here for actual column differ from our assumptions in our previous lecture. And besides the pin jointed end connections that we assumed, other type of end connection can also be there. For example, in figure number B, you see the fixed free column. That is, the column is fixed at one end, whereas it is free at the other end. The column may be fixed at both ends also, or the column may be fixed at one end and pinned at the other end. You can see here for this fixed column, the curvature of the column, that is the bending shape of the column, is different from the fixed pinned column. Since for the fixed end there will be no rotation, the column curvature is somewhat straight near the support points and then bends like this. Whereas that type of curvature is only seen near the fixed end, and in the pinned end rotation is allowed, so we can see some rotation of the column here. So these are other idealized end connections in contrast to the both end pinned connection that we assumed in our previous lecture. So today we will look at the effect of another type of end condition, and we will see the effect of here fixed pinned end connection. That is, one end of the column is fixed and the other end is pinned. And for the remaining cases, you can derive the value of critical load and critical stress in the same way. We will not see the derivation. In fact, in our next lecture, when we talk about the effective length of column, we will only see the formula for these factors here. So today let us investigate this case of fixed pinned column. So in our previous lecture, we had 4 basic assumptions for consideration of an ideal column. Please revisit our previous lecture if you are not familiar with that. Those 4 basic assumptions also applies to this case when you are investigating the critical load of fixed pinned column. So we have a similar diagram here, but this time for a fixed pinned column. The first is the unbuckled column. The second figure number B, shows us the buckled shape of column, and in figure number 4 and 3 we have the free body diagram. The free body diagram of entire column is shown in figure C. You can see that in that end where our end is fixed, all 3 types of reactions are being developed. One is the horizontal force, another is the vertical force, and another is the moment. Whereas because of the equilibrium of moment, you can see that a horizontal force Hp is developed as a reaction at the pinned end. Remember, when we are discussing both end as pinned, or you can also say both end as hinged, you saw that in that case there was no horizontal reaction at the pinned end, but in this case we have a horizontal reaction Hb developed at the pinned end. So you can cut a cross section anywhere in your column, and you can draw the feed body diagram of either the upper section or the lower section. Here you can see the free body diagram of partial column, that is of the upper part towards the pinned end here. So the vertical or axial compressive force that is acting on our column is P. The horizontal reaction at the pinned end is HB. We have taken the x-axis is the axis along the longitudinal axis of our column, that is the vertical case here, and we have chosen the y-axis in the horizontal direction. So if we consider this end when we have made the cut to be O, the shear force that develops in this section is Vx and the moment is Mx. The displacement of this end is given as small Vx. So if you again compare with our previous lecture, at the cut end there was only axial force P and there was no development of the shear force. But now, because of this horizontal force HB here, we will also have some shear force acting within the cross section of our column. So let me draw the diagram again. We had this sort of diagram. Here we had the P force. Here we had the horizontal force HB. Here we had the shear force capital Vx. And we had the moment is Mx. And the displacement of this end was small Vx. Sorry. So if you use the principles of static equilibrium, you can get the value of your reactions here. So if you use summation of forces in x equals to 0, you will get the value of Ax as P. That means if you look at your diagram, Ax gives us this value of vertical reaction here. This we get as P. And if you sum all the moments about the point A and equate them to 0, you will get the value of By as Hb. That means if you go to your previous, this we have got as Hb here. This is the horizontal reaction at point B, By, and the arrow is showing the sense of this force here. So this you got, in fact, to find these reactions here, Ax and By, you do not need the free body diagram of partial column. You can do that from the free body diagram of entire column. So when you consider the free body diagram of partial column and sum all the moments about O, that is this section here, and equate them to 0, you will get the value of moment as L minus x into Hb minus P into Vx. Since this length we have is L minus x, the moment due to this horizontal reaction Hb is given as Hb into L minus x, and this is in anticlockwise direction. And also, when we are talking moment about this point O here, the moment due to the force P is clockwise. So we use the negative sign here, and clockwise moment of P is given as P into this horizontal displacement, which is given as small Vx. So we get the moment at any section here, Mx. We put the value of this Mx in our moment curvature equation, which we discussed is Ei V double prime x equals to M. So if you put this into this equation and rearrange the terms, you will get this equation here. Ei V double prime x plus Pvx. You take this Pvx to the left hand side in this equation. So plus Pvx into, open this bracket here, Sbl minus Sbx. So we will again use this notation here, lambda square, which is given as P by Ei. Divide both sides of our equation by Ei here. Then we will get the equation as V double prime plus lambda square V, and this term on the right hand side. Remember, in our previous lecture we got this equation as V double prime plus lambda square V equals to 0, and this was our homogeneous linear second order ordinary differential equation. But now, since we have got some term on the right hand side here, our ordinary differential equation is not homogeneous. Now it has become non-homogeneous. So this is a non-homogeneous linear second order ordinary differential equation with constant coefficients. And the boundary conditions, we have three boundary conditions here. These two boundary conditions are similar to our previous derivation, that is, the displacement at two ends at L equals to 0 and L equals to L is 0. And another boundary condition owing to the fixed end here is that the slope of the fixed end is also 0. So V prime 0 is given as 0. So we have to solve this differential equation with the help of these boundary conditions. So what will be the solution of our differential equation? Let me write our differential equation here once again. So this is V double prime plus lambda square V is given as HB, let me check it whether it is L or X, HBL over EI minus HBX over EI. So we know that the solution of this non-homogeneous equation is a combination of two solutions. One is the complementary solution and another is the particular solution. To get this complementary solution, we just have to put the right hand side term, instead of whatever is here, we have to replace it by 0. When we put the right hand side of the differential equation equal to 0, we get the complementary solution. Then our equation becomes V double prime plus lambda square V equals to 0. So instead of V here, let me give here subscript C that represents this is a complementary solution equation. And we know the solution to this equation as we derived in our last video lecture. The complementary solution is now given as C1 sin lambda x plus C2 cos lambda x. Remember in our previous lecture, after we derived this solution, we used the boundary condition and determined the value of C1 and C2. But in this case, we are still to find this particular solution here. So when we find the total solution, that is this both complementary and particular solution, then only we have to use the boundary conditions. You cannot use right away after this complementary solution. Now let us find the particular solution. To find the particular solution, let us look at this right hand term here. We see that we have two terms in the right hand side. One is a constant term and another is a term which is linear in x. So what we will assume is that our particular solution also consists of two terms, one of which is constant and another is linear in x. So we can write the particular solution as C3, which is a constant term, plus C4 into x, which is a term linear in x. Now if you take the first derivative of this term with respect to x, you will get it. This C3 will reduce to 0, so you will get it C4. Again, if you take the derivative of this term with respect to x, you will get the double derivative of Vp equal to 0. Then we get this value here. If our particular solution is this, what we can say is that it satisfies this equation. Vp double prime plus lambda square Vp equals to HBL by EI minus HBX by EI. We simply put Vp instead of V in our differential equation. Similar to what we did for our complementary solution here, we used Vc instead of only V. Now substitute the value of V double prime P and Vp. V double prime P is 0, so this term will be 0, and Vp is C3 plus C4x. So lambda square is P by EI, Vp is C3 plus C4x, which is equal to the right hand side terms, that is HBL by EI minus HBX by EI. Now this EI terms will be cancelled, and this when we take this P to the right hand side, they will go to the denominator here. So if you compare the individual terms, you can find the equation here. This constant term should be equal to this constant term, so the value of C3 is given as HBL by P, and this constant term should be equal to this constant term, so the value of C4 will be given by HBX by P here. Okay, let me check whether it is positive or negative. Since we have negative here, let us just write negative. So C3 will be equal to this constant term HB into L by P, and C4 will be equal to this term, the remaining term except this X here, minus HB by P. So C4 will be minus HB by P. So I think you can remove this X also here. So this will just be minus HB by P. So we got the value of constant C and 4. Now we have got our total solution. Our total solution will be Vx is our complementary solution, which is given as C1 sin lambda x plus C2 cos lambda x plus HBL by P minus HB by P into x. Since C3 plus C4x is our particular solution, the value of C3 is HBL by P and the value of C4 is minus HB by P, so minus HB by P, and this x came from this same x that we have here. Not from the value of C4, but from this x. Whatever x is here, we put that x here. So this will be our total solution. So this solution you can also find on your next slide here. We have derived first the particular solution and then the total solution. So we first write here the particular solution and then the complementary solution. Now let's see here how many constants we have in this solution here. One constant is C1, another constant is C2, and do you see any other constants here? We have the value of P, we have L, we have X. So you can also say that for a given load, this HB will also be a constant. In fact, this lambda is also constant since lambda square is P by EI, and for a given load, lambda square will be constant. So now use the boundary conditions to get the value of these constants. First, we know that V0 is equal to 0. That is, the displacement at the fixed end is equal to 0. If you use this value in this above equation here, this term will be reduced to 0 since x equals to 0. This term will reduce to 0 since sin 0 is 0, and this term will be 0 since V0 is 0. So the value of C2, this cos lambda x will be 1. So the value of C2 you get is minus HBL by P when you take it to the left hand side. This is the value of C2. Similarly, if you take the derivative of this equation once with respect to x and then use the value of V prime 0 equals to 0, you can get the value of C1, which you get is HB over lambda P. I have not shown the detail here, you can just calculate it yourself. If you take its first derivative, V prime x, this is a constant, so it will be 0. This will be minus HB by P. C1 lambda x will be changed to plus C1 lambda into cos lambda x. We know the value of C2 here, minus HBL by P, and cos lambda x will be minus lambda sin lambda x, so minus minus plus sin lambda x. Now if you put x equals to 0, this whole term will be 0 since sin 0 is 0. This whole term will be C1 into lambda since cos lambda 0 will be 1, and this will be 0. So if you take it to the next side, you will get the value of C1 as HB by lambda P. So this is our value of our constant. And finally, when you use this VL equals to 0, you will get this equation here. When you use x equals to L here, this term and this term will be the same, so they will cancel, and the remaining is C1 lambda L plus C2 lambda L equals to 0. Thus, we get these three equations using our boundary conditions. So what happens if you combine these three equations? We have C1 lambda L plus C2 cos lambda L equals to 0. So let us write the value of C1 sine lambda L plus we have got the value of C2 is minus HB by LP into cos lambda L equals to 0. So we can write this as C1 sine lambda L. If we want these terms in terms of C1, what we can do is we can add lambda here and lambda above also, so that this HB by P lambda will be equal to C1. Thus we can write this as minus C1 remaining lambda L into cos lambda L equals to 0. Take C1 common, you will get this equation here. So combining the above three equations, we got this equation here. So our C1 is not equal to 0. If C1 is equal to 0, then this means that this HB should also be equal to 0 and the value of C2 then should also be equal to 0. So that is a trivial solution that only represents the straight condition of your column. We do not have any deflections there. So to get alternate solution, the remaining term should be equal to 0. Sine lambda L minus lambda L cos lambda L equals to 0. So alternate equilibrium configurations are possible if lambda satisfies the following equation. The same equation, after removing C1, we put this subscript n in lambda here. So if you rearrange the equation and divide both sides by cos lambda L, you will get the value of tan lambda nl equals to lambda nl. The value of n is 1, 2, 3 and others. So this equation is called the characteristic equation. It has an infinite number of solutions, but as in the case of pinned column, we are only interested in the smallest value of lambda L that satisfies the above equation. Remember in our previous lecture when we discussed about the mode shapes, when we kept n equals to 1, our deflection of column was like this. When we kept n equals to 2, our deflection of column was represented by this curve here. So n equals to 1 represents that smallest value of load for which this equation is satisfied, and also that load will be equal to the critical load, because critical load means the smallest value of the load that causes the column buckling. So how can we solve this equation here? One way to solve this equation is plot two graphs. First graph you plot tan lambda L versus lambda L, and second graph you plot lambda L versus lambda L. So the smallest value of lambda L where the curve intersects f lambda L and g lambda L, this is given by lambda 1 L equals to 4.4934. So we have named this tan lambda L function as f lambda L, and we have named this lambda L function as g lambda L. So the point where this f lambda L and g lambda L intersects will give us the smallest value of lambda L. That smallest value, if we draw the graph and find the intersection point, will come out to be 4.4934. So this is the smallest value of lambda 1 L or lambda L which satisfies the above equation. Using this value, now let us find the value of critical load here. We know that lambda square is given as P by EI. If you get the value of lambda 1 from here, that will come out to be 4.4934 divided by L. So to get the value of PCR, lambda square into EI, that means 4.4934 over L square into EI. This square is nearly equal to 20.19 EI over L square. So this is our critical load for the column that we are discussing now, that is the fixed and pinned column. If you want to compare this critical load to the critical load value that you obtained for pinned column, remember we got PCR as pi square EI over L square for our first case. This is for our second case. If you want to find the differences, This 20.19 minus this lambda square, since other terms are the same, divided by the initial coefficient pi square into 100. This will nearly come out to be 105%. So you can say how great a load is required to buckle our fixed pinned column in contrast to our pinned column. So this is just for checking the different value of critical load. You do not need this right now. Just remember that this is the formula that we have derived for fixed and pinned column. So what is our conclusion? We see that the elastic buckling of any column can be expressed as some constant times the factor EI by L square. For example, for pinned column, it was pi square into EI by L square. For our fixed pinned column, we got is 20.19 into EI by L square. So that means for all of the columns, the elastic buckling load can be expressed as some constant times the EI by L square. So all of the comments regarding the effect of parameters E, I and L on the buckling of pinned column also hold true of columns with other end conditions. That means our critical load, since we have the always same factor here, our critical load will always be directly proportional to this flexural rigidity and inversely proportional to the square of the length. So these are the comments that will be same for all types of columns. In fact, using these characteristic buckling equations, we can derive many comments or we can derive many different relations. So let me discuss one or two with you in a quick fashion. So using or seeing this equation, what you can see is that the only material property that enters directly into either the elastic buckling load or the buckling stress. So we derived sigma CR also in our previous lecture. So the only material property that enters into these equations is this modulus of elasticity, and this modulus of elasticity represents the stiffness of the material. So if we want to increase the elastic buckling load of any member, one of the way is to use a material with high value of modulus of elasticity. That is one of our conclusions. The second conclusion is that the elastic buckling load is inversely proportional to the square of the length of the column, as we have already discussed here. A third conclusion or a third comment is that the buckling load can be increased by increasing the value of the cross-sectional moment of inertia. Since we have I in the numerator here, we can say that our buckling load is directly proportional to cross-sectional moment of inertia, assuming all other factors remain constant. So if we want to increase the buckling load, we can increase this value of moment of inertia. And one way to increase this value of moment of inertia is by using thin tubular members. For example, this circular column, if we are using, we can use a member with thin wall so that our cross-sectional moment of inertia is increased. However, one thing to remember when we are using these thin-walled columns is that the thickness of the wall should not be so thin that local buckling can occur. So you have to differentiate between global buckling and local buckling. Our thickness of the column section should not be so small that there may occur local buckling. So that local buckling will induce a failure in our columns also, so we must make sure of that too. And we talked about how, as a fourth comment, we talked about this in our previous lecture also, our Euler's formula is valid only for long columns, that is columns whose slenderness ratio, that means L by R ratio, leads to a critical stress below the compressive proportional limit, or for our case compressive yield stress, as we saw in our previous lecture diagram at last when we discussed a diagram regarding L by R and sigma CR for two materials. One was steel material and another was aluminum material. This equation is valid only for a value of sigma y. Above this compressive stress or compressive yield stress, our formula is not valid. So these are some of the comments or some of the conclusions of our formula that we have derived, and these are applicable to both our pinned column and fixed pin column also. Finally, to determine the buckling mode of the fixed pin column, we derive this equation of Vx here. Use the value of all constants, then you will get this value of Vx, and this represents the buckling mode of our column. For a pinned column, the buckling equation or our mode shape was just given as C into sine, I guess it was pi x by L or something like that, for n equals to 1, and we got a simple sine curve. And I forgot to tell you in our previous lecture, but this C represents the magnitude and direction of our deflection. And this curve that is given here represents the mode shape. So we got a complex mode shape or buckling mode for our fixed pin column here. And the fundamental buckling mode is shown in the diagram here also. So this is not a totally good sine curve or perfect sine curve, but there are some variations owing to the formula that we derived here. So here in this formula you can see that the effective length is equals to 0.70 L. This concept of effective length we will discuss in our upcoming lecture. So this is about the buckling load for an ideal fixed pin column. So in this lecture we discuss the effect of end conditions on the buckling load of a column, and we saw in detail about the buckling load, and we derived the formula and buckling mode shape also for the ideal fixed pin column. In our next lecture, in the beginning we will very shortly see about the concept of effective length, and if possible we will also do a numerical regarding the buckling of a columns. So we'll meet again soon in our next lecture. Till then, stay safe and thank you.